In the mathematical discipline of set theory, forcing is a technique discovered by Paul Cohen for proving consistency and independence results. It was first used, in 1963, to prove the independence of the axiom of choice and the continuum hypothesis from Zermelo-Fraenkel set theory. Forcing was considerably reworked and simplified in the following years, and has since served as a powerful technique both in set theory and in areas of mathematical logic such as recursion theory. Descriptive set theory uses the notion of forcing from both recursion theory and set theory. Forcing has also been used in model theory, but it is common in model theory to define genericity directly without mention of forcing. Intuitions. Forcing is equivalent to the method of Boolean valued models, which some feel is conceptually more natural and intuitive, but usually much more difficult to apply. Intuitively, forcing consists of expanding the set theoretical universe V to a larger universe V**. In this bigger universe, for example, one might have lots of new subsets of omega equals 0, 1, 2, that were not there in the old universe, and thereby violate the continuum hypothesis. While impossible on the face of it, this is just another version of Cantor's paradox about infinity. In principle, one could consider identify with, and then introduce an expanded membership relation involving the new sets of the form. Forcing is a more elaborate version of this idea, reducing the expansion to the existence of one new set, and allowing for fine control over the properties of the expanded universe. Cohen's original technique, now called ramified forcing, is slightly different from the unramified forcing expounded here. Forcing posets. A forcing poset is an ordered triple, whereas a preorder on P that satisfies following splitting condition. For all P, there are Q, Rp such that Q, Rp with no Sp such that Sq. The largest element of P is 1, that is, P1 for all Pp. Members of P are called forcing conditions or just conditions. One reads PQ as P is stronger than Q. Intuitively, the smaller condition provides more information, just as the smaller interval 3.1415926, 3.1415927 provides more information about the number pi than the interval 3.1, 3.2 does. There are various conventions in use. Some authors require to also be antisymmetric, so that the relation is a partial order. Some use the term partial order anyway, conflicting with standard terminology, while some use the term preorder. The largest element can be dispensed with. The reverse ordering is also used, most notably by Saharan Scheller and his co-authors. P-names associated with a forcing poset P is the class 5 of P-names. P-names are sets of the form U is a P-name and P-P-n. Using transfinite recursion, one defines name equals the power set of times P. Name equals name. Alpha less than lambda for lambda a limit ordinal, and then the class of P-names is defined by V equals name. Alpha as an ordinal. The P-names are, in fact, an expansion of the universe. Given xv, one defines x to be the p-name x equals yx. Again, this is really a definition by transfinite recursion. Interpretation. Given any subset G of P, one next defines the interpretation or valuation map from p-names by val equals val. Pg, U. Note that if one is in G, then val equals x. One defines G equals pp, so that val equals g. Example. A good example of a forcing poset is I, where I equals 0, 1, and Borel are the Borel subsets of I having non-zero Lebesgue game measure. In this case, one can talk about the conditions as being probabilities, and a Borel name assigns membership in a probabilistic sense. Because of the ready intuition this example can provide, probabilistic language is sometimes used with other forcing posets, countable transitive models and generic filters. The key step in forcing is, given a ZFC universe V, to find appropriate G not in V. The resulting class of all interpretations of P names will turn out to be a model of ZFC, properly extending the original V. Instead of working with V, one considers a countable transitive model M with M. By model, we mean a model of set theory, either of all of ZFC, or a model of a large but finite subset of the ZFC axioms, or some variant thereof. Transitivity means that if X, Y, M, then X, M. The Mostovsky collapsing theorem says this can be assumed if the membership relation is well-founded. The effect of transitivity is that membership and other elementary notions can be handled intuitively. Countability of the model relies on the Lowenheim-Skolem theorem. Since M is a set, there are sets not in M. This follows from Russell's paradox. The appropriate set G to pick, and adjoined to M, is a generic filter on P. The filter condition means that GP in 1G. If PQG, then PG. If PQG, then RG, RP and RQ. For G to be generic means if Dm is a dense subset of P, then GD0. The existence of a generic filter G follows from the Razor-Auer-Sikorski lemma. In fact, slightly more is true. Given a condition P, one can find a generic filter G such that PG. Due to the splitting condition, if G is filter, then PG is dense. If G is in M, then PG is in M because M is model of set theory. By this reason, a generic filter is never in M. Forcing. Given a generic filter GP, one proceeds as follows. The subclass of P names in M is denoted M. Let Mg equals val UM. To reduce the study of the set theory of Mg to that of M, one works with the forcing language, which is built up like ordinary first-order logic, with membership as binary relation and all the names as constants. Define P phi where P is a condition, phi is a formula in the forcing language, and the area names, to mean that if G is a generic filter containing P, then Mg phi val. The special case 1 phi is often written P phi or phi. Such statements are true in Mg, no matter what G is. What is important is that this external definition of the forcing relation P phi is equivalent to an internal definition, defined by transfinite induction over the names on instances of UV and U equals V, and then by ordinary induction over the complexity of formulas. This has the effect that all the properties of Mg are really properties of M, and the verification of ZFC in Mg becomes straightforward. This is usually summarized as three key properties. Truth. Mg phi val, if and only if it is forced by G, that is, for some condition Pg, P phi. Definability. The statement P phi is definable in M. Coherence. If P phi and Qp, then Q phi. We define the forcing relation in by induction on complexity, in which we simultaneously define forcing of atomic formulas by induction and then we define it by induction on formula complexity. 1 if, 2 if, 3 if, 4 if, 5 if. In 1 to 5 is an arbitrary condition. In 1 and 2 are arbitrary names, and in 3 to 5 are arbitrary formulas where all three occurrences are variables referring names. This definition is syntax transform of formulas. This means that for any given formula the formula with free variables is well defined. In fact, this syntax transform has following properties. The bit of definition is existence of syntax transform with these properties. This definition provides the possibility of working in without any countable transitive model. The following statement gives announced definability, where means that is countable transitive model satisfying some finite part of axioms depending on formula. Consistency. The above can be summarized by saying the fundamental consistency result is that given a forcing poset P, we may assume that there exists a generic filter G, not in the universe V, such that V, G, is again a set theoretic universe, modeling ZFC. Furthermore, all truths in V, G can be reduced to truths in V regarding the forcing relation. Both styles, adjoining G to a countable transitive model M or to the whole universe V, are commonly used. Less commonly seen is the approach using the internal definition of forcing, and no mention of set or class models is made. This was Cohen's original method, and in one elaboration, it becomes the method of Boolean valued analysis. Cohen forcing. The simplest non-trivial forcing poset is 0. The finite partial functions from omega to 2 equals 0, 1, under reverse inclusion. That is, a condition P is essentially two disjoint finite subsets P-1, 1, and P-1, 0 of omega, to be thought of as the yes and no parts of P, with no information provided on values outside the domain of P. Q is stronger than P means that QP, in other words, the yes and no parts of Q are supersets of the yes and no parts of P, and in that sense, provide more information. Let G be a generic filter for this poset. If P and Q are both in G, then PQ is a condition, because G is a filter. This means that G equals G is a well-defined partial function from omega to 2, because any two conditions in G agree on their common domain. G is in fact a total function. Given n omega, let Dn equals P. P is defined, then Dn is dense. A condition PG_Dn has n in its domain, and since PG, G is defined, let X equals G-1, 1, the set of all yes members of the generic conditions. It is possible to give a name for X directly. Let X equals P equals 1, then val equals X. Now suppose A omega in V. We claim that XA. Let dar equals P, n, ndom and P equals 1 if and only if NA, dar is dense. Then any PG dar witnesses XA. To summarize, X is a new subset of omega, necessarily infinite. Replacing omega with omega times omega 2, that is, consider instead finite partial functions whose inputs are of the form, with n less than omega and alpha less than omega 2, and whose outputs are 0 or 1, one gets omega 2 new subsets of omega. They are all distinct, by a density argument. Given alpha less than beta less than omega 2, let d alpha, beta equals p, n, pp, then each d alpha, beta is dense, and a generic condition in it proves that the alpha th new set disagrees somewhere with the beta th new set. This is not yet the falsification of the continuum hypothesis. One must prove that no new maps have been introduced which map omega onto omega 1 or omega 1 onto omega 2. For example, if one considers instead finite partial functions from omega to omega 1, the first uncountable ordinal, one gets in V, G, a bijection from omega to omega 1. In other words, omega 1 has collapsed, and in the forcing extension, is a countable ordinal. The last step in showing the independence of the continuum hypothesis, then, is to show that Cohen forcing does not collapse cardinals. For this, a sufficient combinatorial property is that all of the antichains of this poset are countable. The countable chain condition. An antichain A of P is a subset such that if P and Q are in A, then P and Q are incompatible, meaning there is no R in P such that Rp and Rq. In the Borel sets example, incompatibility means PQ has measure 0. In the finite partial functions example, incompatibility means that PQ is not a function. In other words, P and Q assign different values to some domain input. P satisfies the countable chain condition if every antichain in P is countable. It is easy to see that Borel satisfies the C, because the measures add up to at most 1. Fin is also C, but the proof is more difficult. Given an uncountable subfamily W fin, shrink W to an uncountable subfamily W0 of sets of size n, for some n less than omega. If P equals B1 for uncountably many PW0, shrink to this uncountable subfamily W1, and repeat, getting a finite set and an uncountable family weak of incompatible conditions of size n-k such that every E is in at most countably many DOM for P weak. Now pick an arbitrary P weak, and pick from weak any Q that is not one of the countably many members that have a domain member in common with P. Then P and Q are compatible, so W is not an anti-chain. In other words, fin anti-chains are countable. The importance of anti-chains in forcing is that for most purposes, dense sets and maximal anti-chains are equivalent. A maximal anti-chain A is one that cannot be extended and still be an anti-chain. This means every element of PP is compatible with some member of A. Their existence follows from Zorn's lemma. Given a maximal anti-chain A, let D equals P. PQ, sum QA, D is dense, and GD0 if and only if GA0. Conversely, given the dense set D, Zorn's lemma shows there exists a maximal anti-chain AD, and then GD0 if and only if GA0. Assume P is C, C, C. Given x, y, v, with f, x, y and v, g, one can approximate f inside v as follows. Let U be a name for f and let P be a condition which forces U to be a function from x to y. Define a function f whose domain is x by f equals b. Q forces U equals b. By definability of forcing, this definition makes sense within V. By coherence of forcing, different B's come from incompatible P's. By C, F is countable. In summary, F is unknown in V, since it depends on G, but it is not wildly unknown for a C. Forcing. One can identify a countable set of guesses for what the value of f is at any input, independent of G. This has the following very important consequence. If in V, G, F, alpha beta is a surjection from one infinite ordinal to another, then there is a surjection G, omega times alpha beta in V and consequently a surjection H, alpha beta in V. In particular, cardinals cannot collapse. The conclusion is that 2 in V, G, Easton forcing, the exact value of the continuum in the above Cohen model, and variants like fin for cardinals kappa in general, was worked out by Robert M. Solovay, who also worked out how to violate GCH, for regular cardinals only, a finite number of times. For example, in the above Cohen model, if CH holds in V, then 2 equals 2 holds in V, G. WB. Easton worked out the infinite and proper class version of violating the GCH for regular cardinals, basically showing the known restrictions were the only ZFC provable restrictions. See Easton's theorem. Easton's work was notable in that it involved forcing with a proper class of conditions. In general, the method of forcing with a proper class of conditions will fail to give a model of ZFC. For example, fin, where on is the proper class of all ordinals, will make the continuum a proper class. Fin will introduce a countable enumeration of the ordinals. In both cases, the resulting V, G, is visibly not a model of ZFC. At one time, it was thought that more sophisticated forcing would also allow arbitrary variation in the powers of singular cardinals. But this has turned out to be a difficult, subtle and even surprising problem, with several more restrictions provable in ZFC, and with the forcing models depending on the consistency of various large cardinal properties. Many open problems remain. Random rails. In the Borel sets I example, the generic filter converges to a real number I called a random real. A name for the decimal expansion of R can be given by letting R equals E equals k 10 minus n, 10 minus n, 0 k less than 10 n. This is, in some sense, just a subname of G. To recover G from R, one takes those Borel subsets of I that contain R. Since the forcing poset is in V, but R is not in V, this containment is actually impossible. But there is a natural sense in which the interval 0.5, 0.6 in V contains a random real whose decimal expansion begins 0.5. This is formalized by the notion of Borel code. Every Borel set can, non-uniquely, be built up, starting from intervals with rational endpoints and applying the operations of complement and countable unions, a countable number of times. The record of such a construction is called a Borel code. Given a Borel set B in V, one recovers a Borel code, and then applies the same construction sequence in V, G, getting a Borel set B asterisk. One can prove that one gets the same set independent of the construction of B, and that basic properties are preserved. For example, if B C, then B asterisk C asterisk. If B has measure 0, then B asterisk has measure 0. So given R, a random real, one can show that G equals B, R B asterisk. Because of the mutual interdefinability between R and G, one generally writes V, R, for V, G. A different interpretation of rails in V, G, was provided by Dana Scott. Rational numbers in V, G, have names that correspond to countably many distinct rational values assigned to a maximal anti-chain of Borel sets. In other words, a certain rational valued function on I equals 0, 1. Real numbers in V, G, then correspond to Dedekind cuts of such functions, that is, measurable functions. Boolean valued models. Main article. Boolean valued model. Perhaps more clearly, the method can be explained in terms of Boolean valued models. In these, any statement is assigned a truth value from some complete atomless Boolean algebra, rather than just a true, false value. Then an ultrafilter is picked in this Boolean algebra, which assigns values true, false to statements of our theory. The point is that the resulting theory has a model which contains this ultrafilter, which can be understood as a new model obtained by extending the old one with this ultrafilter. By picking a Boolean valued model in an appropriate way, we can get a model that has the desired property. In it, only statements which must be true will be true, in a sense. Meta-mathematical explanation. In forcing, we usually seek to show some sentence is consistent with ZFC. One way to interpret the argument is that we assume ZFC is consistent and use it to prove ZFC combined with our new sentence is also consistent. Each condition is a finite piece of information. The idea is that only finite pieces are relevant for consistency. Since by the compactness theorem a theory is satisfiable if and only if every finite subset of its axioms is satisfiable, then, we can pick an infinite set of consistent conditions to extend our model. Thus, assuming consistency of set theory, we prove consistency of the theory extended with this infinite set. Interval 3.141596, 3.141597 provides more information about the number pi than the interval 3.1, 3.2 does. There are various conventions in use. Some authors require to also be antisymmetric, so that the relation is a partial order. Some use the term partial order anyway, conflicting with standard terminology, while some use the term preorder. The largest element can be dispensed with. The reverse ordering is also used, most notably by Saharan ramified forcing expounded here. Forcing posets. A forcing poset is an ordered triple, whereas a preorder on P that satisfies following splitting condition. For all P, there are Q, Rp such that Q, Rp with no Sp such that Sq. The largest element of P is 1, that is, P1 for all Pp. Members of P are called forcing conditions or just conditions. One reads PQ as P is stronger than Q. Intuitively, the smaller condition provides more information. Just as the smaller a theory, forcing has also been used in model theory, but it is common in model theory to define genericity directly without mention of forcing. Intuitions. Forcing is equivalent to the method of Boolean valued models, which some feel is conceptually more natural and intuitive, but usually much more difficult to apply. Intuitively, forcing consists of expanding the set theoretical universe V to a larger universe V**. In this bigger universe, for example, one might have lots of new subsets of omega equals 0, 1, 2, that were not there in the old universe, and thereby violate the continuum hypothesis. While impossible on the face of it, this is just another version of Cantor's paradox about infinity. In principle, one could consider identify with, and then introduce an expanded membership relation involving the new sets of the form. Forcing is a more elaborate version of this idea, reducing the expansion to the existence of one new set, and allowing for fine control over the properties of the expanded universe. Cohen's original technique, now called ramified forcing, is slightly different from the In the mathematical discipline of set theory, forcing is a technique discovered by Paul Cohen for proving consistency and independence results. It was first used, in 1963, to prove the independence of the axiom of choice and the continuum hypothesis from Zermelo-Fraenkel set theory. Forcing was considerably reworked and simplified in the following years, and has since served as a powerful technique both in set theory and in areas of mathematical logic such as recursion theory. Descriptive set theory uses the notion of forcing from both recursion theory and set